Hello everyone, I'm Bowen. Today I'm excited to present our project ReflectanceFusion, diffusion-based text-to SVBRDF generation. This project is collaborated with Sean from University of California area and Claudia from the University of York, and it's under my guidance of my supervisor Zara. Now we will introduce what and why SVBRDFs. We show varying bidirectional reflecting distribution function. I will assuming that everyone here in this room is familiar with what is SVBRDFs. It comes with lots of benefits such as relevant fast flexibility. SVBRDF maps is used to render images here. It consists of 4 maps: normal, diffuse, roughness, and specular. The question remains, how do we actually generate or query these SVBRDF maps? There are several professional software available for designing SVBRDFs, including Substance Designer, 3D Max, and others. However, it's important to know that the operation of these tools is complex and demand a certain level of professional knowledge and skills. This imagery here demonstrates how Substance Designer design material by using the node graph. It looks like a little bit complex. Another way to create SVBRDF is through dense sampling. They start with collecting detailed images of real-world materials. We use a high-quality camera to take pictures of the material from different angles and varying light conditions to capture the surface detail. This procedure needs precise equipment. It looks like very expensive here. And also need a lot of time to do the sampling. After collecting this data, we then extract the SVBRDFs. This approach tends to be very time-consuming. And another approach involves using neural network to predict SVBRDF from a single image. A lot of recent work have been done on this. While this method can significantly reduce the time and resources needed for data collection, it also faces certain challenges. For instance, the accuracy of the predicted SVBRDF can be limited by the quality of the input images and even limited by the model's ability of the training data. This can result in mismatch between the predict and the actual materials properties. Furthermore, this is an uncertainty in SVBRDF generated by one single images of the neural network. A single materials can be associated with multiple possible SVBRDFs. And based on the previous research gaps, we propose our motivations here. First, we want a fast performance systems. Instead of using hours to collecting or sampling the data, could we do it in 10 seconds? And user-friendly. You don't want to learn this complex software. Could we use text-controlled generation? And also the powerful capability of generating complex SVBRDFs. So here is our ideal pipeline. We have the text input to the model, and just within 10-second calculation, it gives us the result back. And we can generate it multiple times, and we choose which we want, and then rendering our 3D materials. Next, I will introduce the methodologies. Let me briefly introduce the diffusion model. Diffusion model is a model that turns text into images. It works by gradually transforming random noise into images. This procedure is guided by a neural network that we learned from the dataset of the text and image pairs. This model starts with noise and gradually refine this noise into image, then that matching the text descriptions. However, it's designed only for making the images from the text and isn't suitable for rendering tasks. Diffusion model is have 3 components. The middle part is the core part UNet, and the left and the right part is the VE encoder and decoder. The VE full name is the variation or encoder. It's a type of artificial network can convert the input to the latent space and then convert it back to the image. Our objective is clearly defined on this slides now. The left and the right is our objective. We want the text input, rabbit curved wood as input and the SVBRDF output. Next is time to design the model. We began by considering what we could achieve this by using powerful tools, diffusion models here. Our initial strategy using one stable diffusion frees the main UNet component and train all the decoders. We expect that it enables reconstruct of the SVBRDF from the latent representation by training these new decoders. Thus, we freeze the V encoder and UNet, training all the decoder. We replace the older decoder with a large one, have more neurons and layers, except we have more powerful than previous. But this approach was unsuccessful. When using like the carved wood rabbit as input, it didn't produce some rabbit shapes, but with odd colors and highlight. We trained this method with multiple materials, but the results were consistently fails. The GIF here, the light is moving from top left to the bottom right. Yeah, it's no colors here. And next, instead of freezing both VE encoder and UNet, we choose to freeze only VE and directly train the entire diffusion UNet core part. We anticipating that training the network directly would generate some reasonable SVBRDFs. However, this approach was had to lose the ability to representing complex texture due to limitation number of the training dataset. A directly training diffusion model tend to decline generalization ability. Moreover, as the dataset lack of text label, we need to use a clip model to obtain the texture descriptions, which unfortunately lead to reduced accuracy and further degrade the model's performance. As anticipated, the trained models managed to generate some basic materials like the wood, but they struggle significantly with the target rabbit. There is definitely no rabbit in this wood. Then, considering our desire for generability and the accuracy color representation, we want to maintain the diffusion models untrained due to the limitation of our training data. Basically, we want to follow the UNet and get inspired by stable diffusion XL. We conceived the idea of designing model that have diffusion models operating in series. Here we have the architecture of the stable diffusion UNet part. In the top left and the top right, we input latent variable and predicted noise. The blue sections represent the cross-attention layers, and the down and up blocks are used to modify the neural network resolutions. Then we'll put it here for future uses. Here we continue with our stable diffusion models. We adopt always VE decoders to process latent here, connecting with UNet. In this diagram, we use GREE to integrate this component are frozen, meaning they will not be trained. The purpose of using this model is to enhance the model's perceptual capability, preparing it for next module. Here we utilize the initial layer of the VGG network, specifically VGG16. We discard the later layer of this network. We opt for the initial layer of VGG because they are highly effective at extracting features and content comprehensions. The initial layer of VGG16 are applied to a wide range of image processing tasks, including the perceptual loss. We have choose the output from the 3 blocks of VGG16 to serve as input of our subsequent models. Still, we agree as frozen network. We pass the output from the VE to the VG network in order to extract features. Next, we plan to design the second part of our diffusion models. Given the limited number of the dataset, training a stable diffusion might not proceed normally. Therefore, instead of denoising in the latent space, we perform directly denoising with the SVBRDF space. This approach results in higher computation costs compared to stable diffusion, especially due to the attention whose complexity is quadratic. Doubling the resolution could almost increase the computation burden by 16 times. Consequently, in designing our network, we configure the outer layer on either side to only contain resonant block, which could reduce the computation burden. The intention behind this design is to treat this part of the network as like the VE structure in stable diffusion, effectively compressing resolution to get latent representations. One of our key differences is that our string from end to end and the VE need to be trained separately. Next, we plan to design the second part. Next, we focus on the attention blocks with the network. This their symbols represent modules that include either downsampling or upsamplings. Each of these modules consists of an alternative configuration of the two spatial transformer and the two of the ResNet, followed by an additional upsampling and downsampling modules. The design of this four network block is similar. However, the middle layers differ slightly in structures. It composed just only the spatial transform and the resonant block, but do not include any upsampling and downsampling modules. Then we get our full pipelines here. We have two diffusion models in series. Here I will introduce how we train our model. We use dataset ERAN synthetic dataset and the U-boat dataset. It contains over 200,000 materials in total, and the resolution will be 288. And due to the limitation of the dataset, we choose 256 as our network resolutions. And as I said before, we will freeze the gray part of the network and train the later part end to end. After the training, here is back to our full pipeline here. If we use the rapid curved wood as the input, what can we get? We run it twice, and we get some rapid curved wood shapes and rendering flat surface and in 3D shapes. You can find that there are really some rabbits in the wood. And here comes more result. Firstly, here is the stationary materials. Stationary material have uniform properties, is easily represent statistically and suitable for seamless tiling, whereas non-stationary material display structure varying patterns that are less predictable. We choose some different phenomena materials here, like thick wood, mainly domained by the diffuse map, and the other two have greatly affected by the specular maps. This shows our model's capabilities of generating different types of materials. And this is rendering 3D balls. Here is some non-stationary materials. We challenge our network using some input as the dragon embroidered fabric and the dragon curved wood or the ceramic with specific colors here. And that will give us the correct result. Here is rendering the 3D balls. And also our model capability of generating the metallic materials here. We tried different metals like the gold, silver, and aluminum using shaped dragon and cat. You can see with the light changes, you can notice that there is very significantly metal effects. And also we could achieve the combined materials like metal on the wood and the metal cat with Nike logo on rough leathers. Yeah. And here is a comparison to the previous work. As far as we best our knowledge, until this work is done, there is only one work have been done, the text to material generation is TextMed. And we have asked the author for some result as they didn't publish their code. Thanks to the author here. And obviously they didn't have any dragons in the first one. And even I can't recognize the first one as the wood. And the second one, I think they are fabric and have some cat shape, but it's not perfect as ours. And also for the metal result, ours successfully reproduce the metal effect and they didn't. Yeah, and here are some limitation and future works. We have sometimes in the generated result, we have the big highlight and the shadows, like in these scenarios, within light change, but the shadows constantly stayed here because the shadow is baked in the orbital maps here. And also, so we have the inaccuracy SVBRDFs. We show it in this dragon modded gold result. It don't have any dragon in this SVBRDF maps and don't have the gold-like effect in the specular maps. So the future work will be like to keep improving the network, and we want to achieve the more precise control because just using text to control the network is a little bit weak. And also the higher resolution. Due to the limitation of the resolution, it's just 256, the application scenario will be limited. We expect exploring the better data set like the open SVBRDFs or either using the other super resolution method to achieve the higher resolutions. Thanks for listening.